I'm very excited today to talk to you about word vectors and also release the first problem set, which I think is live now. The people who are uploading it, I think, are uploading it right now in another room. We just talked about it. So that is a big announcement. You can check if, problem set 1 is something that you want to work on. Hopefully, after this lecture today, it'll make a lot more sense. And then we'll give some more details next week as well. But I think after today, you should be able to start tackling problem set 1. We'll also have a coding session. So you get maybe 7 or 10 days or so to really look into it. And then on Monday, you might freak out because it's due on Thursday in 2 weeks. And we'll help you to actually get through some of the code. So there will be a special coding session on Monday, 22nd of January, the Monday of the week that it's due. So it'll be due in 2 weeks from today. Some of the questions on Piazza before we get into any of the details on word vectors, just so we're all in sync. There are a couple of questions around the final project and how many people. In general, ideally, you have one partner for your final project, whether it is problem set 4 or your own project of your own choosing. 2 is the best number. Once it's 3, it's harder to identify who did what exactly. And then like a week before everything is due, we get 2 people who say, oh, this guy, he didn't do anything. And then it's kind of hard for us to deal with it. And so in terms of assignment and alignment, 2 is a good number. Some people are very ambitious, have very ambitious projects. And so if you have a very ambitious project and you can clearly describe why 3 people is necessary, why it's necessary to have 3 people, then you can go ahead and tell us that. And in general, the more epic your projects, the better. So if you have a really cool project, it really warrants 3 people, and it's a success, then everybody is happy. It's tough with one person because it's better to have something that works well with 2 people than something that failed entirely with just 1 person. So just try to avoid that scenario as much as you can. And yes, you can choose a project and have that sort of double count for another class. It comes up a bunch. There are other classes like mining massive data sets. Those massive data sets might be language data sets, and it could make sense to jointly do this. Of course, you have to check with the other class if they're OK with that as well. Likewise, there are a bunch of people who do actual research, and that's fine too. If your research project is aligned with deep learning and NLP, then that's OK too. In some cases, it could be a stretch, like if it's the language of music. We'll have to think a little bit about whether it's really pushing maybe at least on the techniques of deep learning that we've worked on here. Ideally, it really is concretely something with language. And then we went back and forth a little bit on this, but we will allow 1 sheet of notes for the midterm. I don't know. People are already thinking about that. In some ways, I think, well, if it fits on 1 sheet, you can probably also just memorize what's on that 1 sheet. But it will help some people with nerves. And then Azure computing resources, we already got some questions too, which I like. People are thinking forward thinking about this. We'll basically make sure those are available for your projects. And problem set 4, you don't really need it for the first 3 problem sets. They should be possible to be run on a laptop. We will make sure that once you hit the milestone, by that point, in both pset 4 and the final project, regardless of which one you choose, you should have run your first experiments in the cloud. Because for final projects and the problem set 4, you really want to be able to not have things run on your laptop. And then just before your experiment has a breakpoint or finishes training, your laptop dies and you lose like 1.5 days of experiments and so on. We don't want to avoid that. So, and of course, you might not have enough computing power. All right, any organizational questions on the class, the problem set? Yeah?
When will pset 4 be released?
pset 4 will actually release right after PA2 or pset 2 is due. So that way, you'll have a week or 2 to decide and look over that. Think about whether you're excited instead to do your own project and see sort of the trade-offs between, oh, I would now have to select all the data and so on, or I can just start coding actual deep learning NLP methods for pset 4.
When
What is PA1 due Thursday?
Sorry?
What does it say PA1 due Thursday?
Sorry, so this is one we have a little lingo. So PA4 is problem assignment versus PSET. It's the same thing. PSET and PA1 are the same. And basically, we're releasing it today, and it's due in 2 weeks. And that week, the Monday of that week, we'll have the coding session. So it's the week that PA1 is due. Awesome. All right, so let's get started. Today, we will learn about word vectors. It's actually super exciting. There's a lot of people out there who are very excited about word vectors. They're step one for all the things that we're going to do. Right? If you can't understand words, you're not going to be able to understand language or sentences or any of that. It's very fundamental. It's also going to expose you to the first set of math equations that we'll have in the class, and you'll have a lot more of the kind of math that we'll have today in subsequent lectures. So today will be a good way for you to get a sense of like, we'll do some of this interactively, and if you feel like you're getting along and everything's cool, then you're going to be in a good place. If it's too much, you definitely want to start reading up on some of the prerequisites, and if you're bored, I'm sorry, but hopefully you'll at least feel good about yourself and see how all the math skills you learned without knowing what they could be really used for, can be excited that you can use them for really interesting things. So we'll mostly talk about the main method that a lot of people use and get really excited about when it comes to word vectors, called word2vec. It's also really good, I think, in terms of learning about the methods and the equations that we have as a first model to go over. And we'll do a little bit of a refresher on taking gradients very painstakingly and slowly, as well as giving a quick sort of overview of how we actually optimize these models and look at optimization. So how do we represent the meaning of a word? And again, we won't go into too many details about how this has been done in the past. We'll mostly focus on deep learning, but I at least want to give you a sense of why this is so revolutionary or interesting and novel in comparison to the past. And it helps a little bit to at least define the complexity of meaning by these three ways of going about it. And those are, first, you can define meaning as the idea that is represented by a word, as in what is inherently in the word. Second one could be the idea that a person wants to express by using either words or signs or something else, which is the meaning could be the desire that is in the person that's trying to represent something to you. And the third one is the idea that is actually expressed in a work of art in terms of its reception. And there already you see that that might not be the same. Some people think there's inherently a meaning to something. Some people think the meaning that they think about is the important one, and others think that the meaning that is actually received after you communicate is important. So in general, we have sort of this idea of denotation. We have a signifier, some kind of symbol. Again, that could be written language, could be symbols, could be art, could be spoken language, and so on. And you have some kind of thing that is signified. And the relationship between these two we define as denotation. Now, there's a lot of interesting philosophy of language and so on that you could go into, and we won't. Sadly, most of those are not very useful for actually like computationally making sense of this and having computers actually do useful tasks for us. And again, that's going to be our main goal. Now, in the past, most people have used things like WordNet, which is essentially a linguistic resource to define the meaning of words. And WordNet is essentially a very large, we call it taxonomy, or a resource that contains lists of synonym sets and hypernyms. So what are those? So synonym sets, we'll give you an example here. Each word, for instance, good, might have multiple different meanings. And for each synonym set or syn set in WordNet, we might define all the other words that mean the same thing. So in some cases, good can mean full. In other ways, it could be similar to beneficial in meaning, or it could be dear and near, it could be right or ripe, and so on. So good has a lot of different meanings, and each of these meanings has a set of synonyms associated with it. And it could be not just an adjective, but it could also be an adverb, and it could also be a noun. And in each of its meanings, we'll collect these synonym sets or syn sets. So that's sort of the default. Every word is associated with those. And then we connect all these words in what is generally a DAG, a directed acyclic graph. In most cases, it's mostly a tree, but there are some connections in between words. And what that means is we basically give general terms. So the hypernyms are all the words that encompass that particular word and other things. And so, for instance, we can start with all the hypernyms of panda. So panda is, among other things, a carnivore. And all carnivores are placental animals, are placentals. All placentals are mammals, and so on. There's a vertebrate, and all of those are chordates and animals, and then all animals are organisms. Organisms are living things. They're wholes, they're not parts of something. They're objects. They're physical entities in the world compared to mental entities like love and things like that. And in the end, everything in WordNet comes to the top node of the graph, which is an entity. So you might think now, wow, there's a lot to digest. But fortunately, you don't have to really go into this. But it's a useful resource, especially if you just want to look up like synonyms for a specific word. But when we actually want to use this as a resource for downstream tasks, we run into a couple of problems. And the first one is that it's missing a lot of the nuance. So for instance, proficient is listed as its synonym for good. But really, you don't want to go back and forth in all cases. You shouldn't always replace proficient in a sentence with good and to get the same meaning. You'll also have a lot of issues keeping up to date with this resource. So here are just a couple of examples of good that I could come up with, and I'm sure as language evolves, especially with young people, you could come up with even others. But basically, all of these words could nowadays also be synonyms to good and are certainly used. And I'm not going to read all of them, but you can. And they are not in WordNet. And there's no way you can have a single entity that will make sure it's always up to date as a resource. And if you had such a single entity, then it would be very subjective in which words come in and which words don't come in. Of course, there are different dialects, and that will make it even harder. It would require a lot of human labor. We have a really great WordNet resource for English, and then you want to work on French or German. There are actually French and German WordNets, but they're not nearly as big and complete. And you can't actually download the German WordNet. There's some like legal restrictions and so on. So there's a lot of complexity around keeping such a resource alive. And one of the worst issues for us and for downstream tasks is that we don't have a good sense of similarity. You could, in theory, go through this graph and say, well, something is more similar if I only have to go up three levels in the hierarchy here, and then go back down to some other node in this big tree-like structure. But it's a very fuzzy notion, and sometimes 3 steps up goes to like a verb, and it's a completely different kind of word. And so another issue when we just have these discrete representations is, again, with this similarity. Because when they're discrete, the way you would then sensibly describe them as a vector, in the end, we have to give some kind of set of numbers to a computer and to statistical machine learning algorithm to do some kind of computation. They would be represented as so-called one-hot vectors. So one-hot vector, very simple concept. It's essentially a vector that's the length of your vocabulary and has only a single 1 in it for the ID of that word. So every single word gets an ID. Start maybe with aardvark, and then aardvark is the first ID, and so on. And now when you describe, for instance, motel, it'll just be this very large, very sparse vector. Usually you'll have more like 500,000 words in such a vocabulary. And hotel would be this vector. And you can kind of see now that, well, if you wanted to look at the similarity between these two words, there is no similarity between them. But ideally, when you actually do a web search, for instance, you would know that Seattle motel and Seattle hotel should probably give similar results. So we can say that these are essentially orthogonal. The inner product is 0. And there's essentially no natural notion of similarity for these one-hot vectors. And so, again, we could rely on these synonym lists and this tree structure for similarities, but really what we would want is to learn what words are similar in what corpus. You might have certain dialects where these words are quite similar. People use them all the time in similar kinds of ways. And so a big idea, and one of the fundamental ideas of statistical natural language processing that's true for both traditional methods that have thought of this, but especially true for deep learning methods and all the word vectors we'll talk about today, is the distributional hypothesis. Basically, that a word's meaning is given by the words that frequently appear in its context. So in other words, by Firth and several other philosophers have actually described this idea before him, you shall know a word by the company it keeps. So what does that mean? Well, when a word W, which we'll usually assign now as some kind of ID, the ID for a word, appears in a text, then its context is just a set of words that appear nearby. And so what does nearby mean? In most cases, we'll define a window. We'll say a window of 5 words to the left and 5 words to the right of that word, describe it. So very simple. For instance, banking might be described by problems turning into and crises as happened. And for that particular context, we'll define banking as that word, or in that way. Now the question is, how do we actually represent all these other words, which could also just be discrete IDs, into one representation? And the main idea here is that instead of having these discrete one-hot vectors, we'll have a single dense vector representation for each word. And the hope is that, and we'll describe in this lecture how we do this one dense vector representation actually captures the context, all the different contexts that a word might be in. Not just one, but the statistics of all of them. You might get confused sometimes because you'll read in papers, and even in this class, sometimes we call them word embeddings or word representations. They're essentially always word vectors. So just notationally, we'll talk a lot about representation learning and learning embeddings for sentences and things like that. Whenever we talk about word embeddings or representations, we really just mean vectors. They're always dense. They're in the reals. So it's just R to the D. So how does word2vec actually try to capture all these different contexts of a word? How does it actually learn this one representation that summarizes all the contextual words of a single word? The main idea is that you'll have a large corpus of text. So everything is learned in some unsupervised fashion from this text. And then you will look at every single word in that corpus. And for each of these positions, for each word, you will essentially define this word as the center word, the context words as the outside or context words. And then you will use this metric of similarity, the vector representation, to try to predict one from the other. And you'll keep adjusting the vectors to make them better at predicting what those neighboring words are. So let me walk you through an example. So we just mentioned this word banking before. And this is now one such window. So we take a center word. And it starts usually at the first word. But now we've gone through this process a couple times. We look at this center word here at position T. And we want to use the vector of this center word to try to predict, with high probability, which words would appear right next to it. And in most cases, we will not care where exactly the position of these are, as long as they're inside the window. So whether we first predict banking and crises and then turning in problems doesn't really matter. In general, we go from left to right, but it's irrelevant where inside the window they are, as long as they're in the window. So here, you'd have a window size of 2. And you have 2 sets of outside words or context words that you want to predict. So the first one here, for instance, given into our center word, we want to predict problems. So P of WT minus 2, the T is the index again. We step 2 steps to the left. And conditioned now on being our center word, we want to predict that problems would appear in its context. So that's one window at one time of training. And then we move one to the right. Now we will have a different center word, and for that center word, we will want to predict all its context words, again, for this example, where the context size is 2. Okay, does that conceptually make sense? I haven't yet described how we actually compute this probability and how we train the vectors to be good at making this prediction, but that's what we'll define in the next couple of slides. But conceptually, are there any questions around taking this window idea, and now for each word in a large corpus, you download all of Wikipedia, for instance. Wikipedia is actually a good corpus to train these word vectors on because it describes most of human knowledge that people think is important. And we move this window one word at a time, and each time we have a center word in that window, and we try to predict the words to the left and the words to the right. Yeah?
Do we ever try to like weight closer words if we have a big window? Or do we just keep the window small?
Great question. So the question is, do we weigh words differently the closer they are? And people have actually tried this. You might say the window is not just 2, but it's 10. And now maybe the word that is 10 words away is less important, and so we will weigh them differently. People have tried it. It turns out to not matter. In the end, when you have a large enough corpus, you can just assume they're all equally in the context.
You might cover this in the next slide, but I'm assuming you're doing some kind of like max and likelihood.
We'll literally cover that in the next slide, yeah. All right.
Do you ignore punctuation?
Good question. Do we ignore punctuation? Generally, you want to ignore as little as possible, because we would call that pre-processing. And again, we want to go from as raw of a text as possible. In fact, some people try to do this on just characters, but it doesn't work quite as well, and words are actually still quite useful for most applications. But yes, you can use punctuation as well. In fact, punctuation sometimes becomes tricky, and a question of pre-processing when you have hyphenated words. Are they now, should you split them at the hyphen or keep them as a word, and that enlarges your vocabulary? There's a lot of complexity, but we don't have to go there yet.
Those connection words, they carry any kind of meaning, like meaning.
What about connection words and other kinds of, we call them sometimes stop words, and in traditional machine learning methods, we might just ignore them and throw them out. In general, yes, they do carry meaning, and they will give us a lot of hints. So for instance, if you want to do part-of-speech tagging, and you have the before a word, it will help a lot to know in order to understand that what comes after is very likely an adjective or a noun, and very unlikely a verb. So you want to always keep as many of the words with as little pre-processing as possible. And that's a little bit of a philosophical statement, but in general, I think it's true. All right, so we have these windows, and we now move this window across a large corpus of text. Now, how do we formalize this idea of trying to maximize the probability of being able to predict for every center word at position t all its surrounding words? Well, we'll define this as this likelihood. So again, for each position t, from small t1 to capital T, we'll have these probabilities, and we'll just say, okay, we basically multiply for every single position of this large corpus, like Wikipedia. And for every such position, we look at the words that are in m far away. So m here, in this example, was 2. We go basically 2 to the front, and 2 to the left, and 2 to the right. And for each of those positions, we basically want to maximize this probability here. And if this number is very large, then given the context word, given the center word, we're very, very good at predicting the surrounding words. And that means we're kind of capturing the statistics of how these words appear and in which kinds of contexts they appear. Right? So intuitively, for instance, if you have 2 words here that are similar, like Germany and France from that description I showed you in the beginning, then they will probably have very similar kinds of words that appear in their contexts. And if you're able to capture that, that will also make the representation of this WT to be quite similar. OK, now this is the likelihood, but in many cases, we want to minimize a function. And this also has a lot of products. So we basically will take the log of this likelihood, and the negative log, in fact, and then we have the negative log likelihood of this function. The log is a monotonous function, so it doesn't change the minimum. And we'll basically just take the log of this likelihood and minus, and then the two multiplications become sums. And we now have the log probabilities of all of these. And now we want to overall minimize this objective or cost or loss function. We'll use those three terms synonymously. OK, we still don't really know how to compute this probability, but we'll get to that in the next slide. Any questions so far? We're going to in a lot of details, look into how we minimize this function today. So if you are struggling now with the function, now is a good time to ask. OK. Yeah?
So, like, essentially, it's saying you want to multiply the probabilities of each context words appearing. Each of the context words appearing given a certain center word.
So the question is, do we want to maximize the probability that certain words in a context appear given a center word? And yes, that is exactly right.
Okay, so by independent?
They're independently just happening in that window. As long as they're in the window, we don't care if they're in position t minus 2, or t minus 1, or t plus 1, as long as they're in that window around that center word. So we actually call that sometimes a bag of words assumption. So inside this window, all the words are created equal, except, of course, the center word. Mm-hmm.
Consider the likelihood as kind of like a factor probability distribution over all the words.
So do we consider this likelihood as a factor distribution over all the words? So it's certainly not, and we'll get to that, we're not trying to predict the next word like in language modeling, and we'll actually have a whole lecture on trying to predict very accurately the next word. It turns out here, there's not really a connection to language modeling. Sometimes these word vectors will help as pre-training steps, but we don't have to go there yet. So right now, it's really just what I said it is, which is for each position, we're going to try to predict the words surrounding a center word. That's all it tells us. All right. Now, how do we actually compute this probability to get to interesting word vectors that we can then use for a lot of other fun downstream tasks? All right, just copying what we said in the last slide. We want to minimize this objective function. And now the question is, how do we calculate these probabilities? And how do we represent the words so they're not just one-hot vectors? So the first part of that answer is that we'll actually have 2 vectors per word. So every word has 2 vectors associated with it for now. One time when that word is the center word, so we'll call all of those V. And another way is when that word is a context word or is outside in that window around the center word. And we'll call those U. And to make the notation a little clearer, we'll simplify this with this equation. So the probability of an outside word given the center word will be computed with this equation, where we basically take the exponent and we have an inner product between these 2 vectors. And then we will normalize across the entire vocabulary. And we'll say we want to maximize that this word appears given that center word in the window, but we want to basically normalize this to a probability, and we'll sum over all other possible words that could also be there, but aren't. All right, so it's kind of tricky sometimes to wrap your head around this idea that there are 2 vectors now for each word. So we'll look at this picture again, and we'll kind of simplify the notation to make you see the difference. So when we look at into right now, we'll condition this, and this is short form for really we're trying to predict, for instance, in the first step here, problems, the probability, we want to maximize this probability, that problems appears as a word in this context around the center word into, and theta is the list of all the parameters that our model has, and 2 of those parameters are the vector u for problems and the vector v for into, because into is the center word. Now, if we move one to the right, now we'll look at V for banking, and we'll actually have U here for into. Right? So into has, as you just saw, two vector representations. In this case here, it's used as an outside or context word, and so we optimize over U, and here it's the center word, so we have V. Okay, any questions so far? Yeah?
Is this necessary, or is it just an assumption?
It's a good question. Is this really necessary? And it turns out it helps a lot, and I'll go into sort of why it is like that later. To be honest, it's only an intermediate computational trick that we'll use. In the end, we're going to average the two vectors, and we'll have just one vector. But turns out this entire optimization and the math and everything is easier, both in terms of understanding for you, but also for optimizing for the algorithms. So it is a very useful assumption. It's actually how the method is implemented. OK, so two sets of vectors, U's and V's. U's for the context or outside words, V when it's the center word. Yeah.
For the softmax, what were you summing over?
So here, good question. I should have mentioned that. We're actually, in the softmax here, we're summing over V, which is the entire vocabulary. And if you think about that, it's pretty slow, so we'll have some tricks later to actually speed that up computationally. But conceptually, we'll start with that and then look at tricks, and you'll look in pset 1 around tricks for speeding that up. All right, one more question.
Usually, do you have some sort of symmetry between the rows of U and V if you like switch which word plays the center word?
So usually, do you have some kind of symmetry in terms of all the vectors of U and V? When you evaluate them, they actually both capture, in the end, similar kinds of statistics, but they work different, and sometimes for certain tasks, they work better than others. In most cases, the best will be at the very end to just average them again, but let's not worry about that yet. We'll talk about how we use those vectors in the next couple of lectures. All right, so we're moving across this corpus, one window at a time. Each window has a center. We're updating all these weights. So now, how do we actually update the vectors so they're better at capturing which words surround all the other words? So let's dig into this equation a little bit more. So we'll have here our dot product. And intuitively, dot or inner product compares the similarity. So the higher the two vectors dot product is, the more similar those two words are. And again, the more similar they are, the higher that overall probability will be. And after we take all the exponents here, again, we normalize over the entire vocabulary. So this softmax function is actually something you'll encounter all the time. And so we'll ask you to derive its gradients and so on in a lot of details in the homework as well. Homework is a big part of this class. And in general, we'll often write softmax of one element of a longer vector. It's just basically exponentiating all the elements of that vector. And then you have for each element here, this is an Rn to Rn mapping. For each element, you have this. And this is basically the same across all of them. And then we'll write this often as our probability. So if you're a hardcore mathematician and you want to have measure theory and Lebesgue measures and so on, we don't have any of that. When we just have a list of numbers that sums to 1, we're happy enough to call that a probability. So sorry to all the math folks. There's no nice sort of assumptions around like measures and so on for us. Just lists of numbers that sum to 1. All right, now why do we call it softmax? In many ways, basically this exponentiating here maximizes or amplifies that the largest of the elements, but then it is soft because we're not setting all the other elements to 0. So this is going to be used a lot. And most other models out there will have some kind of softmax at the end, and some people actually call it the softmax layer. So in some ways, this is the first layer of what will be very deep neural networks. So definitely think about this function and do problem set 1 to gain familiarity with it. Now, if we wanted to train this model, we would have to take derivatives now with respect to all of these different vectors for all of these different windows. So theta here, which is a set of all the parameters of this model, is essentially one very, very long vector where we stack all the different vectors for each of the words. So we can sort them any way we want as long as it's consistent. But here we have, for instance, all the v vectors first, so when a word is a center word, and then all the context words. So in this case here, we assume each vector is d-dimensional. We have v of them, so it could be 100,000. And so we have 2 times d times v, and that's our gigantic theta vector of all the parameters of this model. Yeah?
The role of the software, is it right that if you drop the exponentiation and just add x over sum x, that would like still be valid in some sense, just wouldn't work very well in the hard documents?
So that would not sum to 1. So you wouldn't have like anything you could call a probability. Right? So without the exponent, you have a bunch of negative numbers here, and then it wouldn't sum to 1. So the exponent is important to get a probability distribution. Mm-hmm.
How do you choose v? Wouldn't it also be a parameter that we need to
How do I choose? Oh, v. Oh, d. Great question. We'll actually have a lot of plots in next week's lecture on evaluating carefully how we choose d. I can give you the short answer, which will almost always be right for any hyperparameter. Hyperparameters are essentially the knobs that you can tune for this. So obviously, the larger d is, the better you'd be able to capture all these contexts, and the the better your model would be to capture which words appear and have correct probability estimates. But then also it gets slower, and so there's a lot of different trade-offs. And in the end, the best answer is you run experiments, you look at a metric, and you see which one works best. And so in most cases, for word vectors, you have them to be between somewhere between 50 to 500. So 95% of all your projects will work well when d is somewhere between 50 and 500. That often gives each vector enough representational power to do well at predicting these probabilities, which then happens to be also good for downstream tasks. OK, so now we know in general what our model is. Our model is we're going through all these windows, we have all these parameters, and want to maximize the probabilities at each time, which is the same as minimizing the negative log likelihood of all of these. And now is the time to actually derive these gradients so we know exactly how to implement this model in math and then later code. So we'll do some interactive whiteboarding, and I'll ask you what the next steps are, and we'll see how quickly we can do it together. So if you're not in the class, maybe we'll have some handwritten notes in the end, but generally it's better if you just watch the videos if you're following the class online. So basically, let's start with the basics. We have here a simple derivative, or the gradient, in fact, of an inner product, x transpose times a with respect to x. And that is actually the same, because there's symmetric here for this inner product as derivative of a transpose x with respect to x, and that's just a. Now, that one is a first one that you should think through carefully, and maybe we'll go over the details when we have some more concrete examples for our model. The second, and probably the most important idea for taking these derivatives properly, is the chain rule. And most of you will think, I know the chain rule, and we'll go through some examples that will look very familiar. But trust me, once you have 5 matrices, and they're all vectors, there's lots of vectors everywhere, and complex matrices, thinking through what that means for the chain rule is still going to be a challenge for at least a quarter of the class. And hopefully, after we go through the lectures and everything, the majority of you will be quite comfortable in taking these gradients. So the chain rule. If you have any kind of function y that you can describe as another function of u, and u can be described as a function g of an actual input, which you can also write as y is f of g of x what that means to now take the derivative of y with respect to x is that we can basically multiply the derivative of y with respect to u times the derivative of u with respect to x. Okay, so that's the abstract standard chain rule. Now let's dive into this a little bit more and look at a very simple example that you should all know from high school. But again, let's just repeat it, and then it'll be more and more complicated. So here, we can rewrite all of this. And it's important sometimes we're just like one step to another is just rewriting something. But the rewriting will make it a lot easier to understand and sort of intuitively see what the next step is. So y, again, we just defined as f of u, so we can rewrite these two very simply. So now let's look at the simple example. You can probably do this without defining any intermediate kinds of variables like u here. But because of that, it's nice to verify that your thinking is correct. So let's say we have dy, or y is this function, and now we want to take the derivative with respect to x of this function. What can we do to use the chain rule? Well, we can define u as g of x to be that center part. So u equals g of x, and that's just what is inside the parentheses. And with this definition of u, f of u becomes 5 times u to the power of 4. Now we can just take the derivative of this function f of u with respect to u, which is just 20 times u to the 3. And we can also, with this definition of u, take the derivative with respect to x, which is just 3 times x squared. All right, so far, so basic high school. And now we just put these two together, and we can define dy dx as dy du times du dx. And that will basically be this. Okay, so that's super simple standard chain rule. I know some people are smirking. I see them in the class. Some, like 1 or 2 are falling asleep. But we want to make sure we're all coming along. All right, so now we're going to actually derive this full softmax probability and for the log likelihood of this function. And we're going to do this for just a single window and a single outside word in that window. So we're not going to go through the entire corpus and keep around all these sums. We're basically going to simplify one instance of this log for one outside word conditioned on one context word. And again, now the center word will be represented with its v vector, and the outside word here will be represented with its u vector. And then you'll have to kind of think through what that means when you actually sum all of these up, and then you sum across all the windows, and so on. So we'll look at one element of this quite gigantic sum, right? If you look at all of Wikipedia, that's a lot of windows. And then for each window, you do at least, with a small window size of 2, you do 4 computations. So it's a lot of computations. But we're going to just look at one such example. And then you actually, in your homework, will combine these and extend it and do a lot of other stuff. All right, so let's write down what these equations are, and then we're going to minimize them together, or compute the gradients, and then we'll also get used to my handwriting, which I apologize already for. All right. Actually, we'll skip that, because I already have it written there. Yeah, it's the same thing. But again, t is the text length, and m is our window size. All right, now we'll write out this main probability.
Richard, is there a way to project what you're writing?
No, but the video should be OK. Is it large enough for people to read in the back? People in the back, give us feedback. All good? OK, I'll try to write larger. All right. So now here, it's important that we sum over and this is a big sum over the entire vocabulary. So our index here is W over all the words in our vocabulary, which again could be like 500,000 or so. So this is a large sum. UW transpose times VC. All right, so that was our probability. And here O and C again are just our word indices. All right, so in order to take the gradients of this, we'll start with taking gradient with respect to our center word. And then you can think about what that means for our context words after. So, and again, remember we actually took the log of this. So I actually have here the log of this, and that equals the log of this whole thing. Okay, so let's write out the derivative with respect to VC of the log of this function. Now, what log of P, O, let's see. Now, what could we do as a first step to simplify when we have a log of this fraction? And we want to get to our VC vector. Yeah?
Log of top minus log of bottom and throughout.
That's right. We can simplify that as writing the following. Take the log first of the top. And we subtract that minus VC of the log of the bottom. Okay, so that already looks a little bit better, right? And now we can basically split this into two steps. We'll start with 1, and then we'll look at 2. Okay, so here we just use the definition almost of the log. Log of A divided by B is log of A minus log of B. All right. So let's look at taking the first derivative. That is quite simple, and I'll ask you in a second why. But we have here the log of the exponent, and we'll assume they have the same basis. So what would be a good next step to simplify that?
Cancel the log.
That's right. We can cancel log an exponent inverse of another. So now we can just write this as UO transpose VC. And now this, if this is like immediately obvious, that's great. For those that are not, we're going to dig in at one last level and go down to taking just the derivative of a single variable by writing this out one more time. And whenever things get kind of gnarly, it's actually a good idea to write things out as indices. It's very simple if you remember vector calculus to do this by just looking at it. But eventually we'll have lots of matrices, there are different layers and so on. So it'll be good to write it out sometimes. So we'll do it here by looking at a single element. So when I write this derivative of something with respect to VC, which is a vector, the context vector, and then have a second subindex here, j, that's just the jth element of that vector. And we can just write UO transpose VC is essentially the same as writing this out as a sum, right? The inner product is just the sum of all the products of all these elements. So that's UO I times VC I. Now, what can we do when we have this kind of sum and we have the gradient operator before the sum?
distribute the gradient into the sum.
That's right. We can swap or distribute it, and that is essentially just the sum here of I equals 1 to d of all of these. You see j times u o I v c I. And then, of course, all of these are just numbers when we're looking at j. So that's just u o j. All right, so this is basically all zeros except for the jth element, which we're looking at here. So whenever you do this, and again, in some cases, those will be matrices. We'll take derivatives with respect to matrices, not just vectors and so on. It's good to write out what these indices are, and then you can kind of see, all right, for one element, and sometimes it's not quite clear yet what happens with more elements, so you can just do it again. You can even make it very explicit, like take the derivative of the first element of the vector and then the second one and the third one, and eventually you'll see a pattern. So here the obvious pattern is that derivative of each of these elements is just one of the elements of the one vector that we took an inner product with. And so what does that mean when we put all of these together and do it for the entire vector? What will be derivative of this? That's right. UO. Cool. All right, so now we have half of the gradients figured out for this. And we can move on to the second and slightly trickier half, where we might also want to use the chain rule and actually apply it in a slightly less trivial example. All right, can I delete this? Okay. I kind of want to use that other side, but it looks a little dark, so it might not be very visible. And we can actually keep this here, because that's what we are going to take the derivative of. All right, so let's look at this second step here. I have the derivative with respect to VC still of the log of the sum over all the vocabulary times the exponent of u w t vc, u transpose. All right, now we want to use the chain rule, and the function that we might want to define here is the log. So let's say we define the log here as our f. And we can define this whole thing as z, where we define g of v of c. In some cases, again, this is so simple, you could just kind of look at it and write it out. But sometimes it's good to also define it, because again, things eventually become so complicated you can't just look at it and see the answer. All right, so now you know, hopefully, the derivative of log of something. So what is the first part of the next line? 1. That's right. 1 over this gigantic sum. W equals 1 to the exponent of u w transpose vc. Now we can multiply this with derivative of vc times the inside of that. And now it's very important, actually, to not use the same index, right? Because this is now a different sum. This is, again, something that's very simple, but it can trip up a lot of people. So it's very important now to change the index here. So we identify that this is a different sum now that sums over also the entire vocabulary, but by itself, independently of this one. All right, so now I have here the exponent of ux transposed vc. And again, when we wanted to use, define this here in terms of the chain rule, then this was essentially the derivative, all with respect to vc, of f of g of vc, where this was our z definition. And this first part was just derivative of f with respect to that z. And now the second part is the derivative of z with respect to vc. Oh, sorry. Actually, derivative of z respect to VC. Yeah. All right. So now this is essentially just a number, right? We can compute it. Now we still need to get rid of the operator here. So let's look into that and now use again the chain rule. So we now have, as the next step, we just carry this one over. So this is still V W equals 1 exponent of U W transpose VC. But now we want to do what we've done before. So what would be the next step? So we have here the derivative of this whole sum. So what can we do? F of z.
The very last slide.
Right here?
Yeah, should have it to the partial the partial. Because if it's partial it's already
Sorry, yeah, this part is just that part.
yeah.
And this is the whole thing.
So I was just pointing out that the first part should be, denominator should be partial z instead of partial vc.
So this is just the like writing up the whole thing. Yeah. F of part v f times v. Oh, I guess you meant that this is not just, oh yeah, this is not just that. This thing. All right, so what's the next step for taking this derivative? Yep,
We take it inside and apply the chain rule.
that's right. We can take the derivative inside. So we have the sum here over x equals 1 to v times the derivative of vc of the exponent of ux transpose vc. And now we again use the chain rule with a different function, namely the function that is the exponent. Right? So we'll have, keep this around, keep the sum around. And now how do we take the derivative of this, where we again apply the chain rule with the exponent function? Somebody else. So this inner product is just a number. What's the derivative of the e to the x? That's right, it's e to the x. So let's just write exponent, or e, to ux transpose vc times the inside, right? So times the derivative of the inside. So this is still vc times ux transpose vc. And now this one is one we've already done. That's just ux. So we can write down the final thing of 2 as the sum over x equals 1 to v times the exponent of ux transposed vc times ux. All right. That was painful, but hopefully to a lot of you, very instructive. So now the question is, what's the last step of putting all of this together and simplifying it a little bit in terms of notation? So let's combine 1 and 2 that we've defined to basically put it all together. And maybe we'll be able to do it all on this slide. Can people see this fine? Should be OK. Looks OK in the video too. All right. So let's put all these equations together. So again, we had the log here of p of o given c. And now the first part of that from the top numerator of the softmax function was just u of o. And we subtracted this big sum here. And now I'm going to write it again just 2 more times to make you see the simplification. Times sum x equals 1 v exponent of ux transpose vc times ux. All right, so what can we do now to basically try to see and maybe bring back that softmax and the probabilities? Well, this one is essentially a number that we can pull into this sum. So we can distribute that term into all of these terms. So we can write UO minus, and this is why it was so important to keep different indices to keep your math correct. You now sum over all of x, and you have this part, exponent of ux transpose vc, and you just keep this one inside here for every single element of that sum. All right, now, hopefully, if you remember all the definitions that we've had, you'll see something that kind of looks familiar in that final equation, which will allow us to write it out much simpler. Does anybody see something we've defined before? That's right, we have a softmax. This is the perfect, nice definition of a softmax where we defined this as exactly the probability of that word x given the center word and its vectors. And we'll just keep ux around here too. So essentially, you can think of this as an expectation, an average over all the different contexts that we have, and you basically want them all weighted by their current, so this is a weighting scheme for this kind of vector. And if you try to minimize this, these vectors will become more and more similar. So in some ways, you could think of this as like the observed thing. So UO is the actual center word. And you subtract all the vectors across the vocabulary based on their probabilities of all these other vectors according to the model currently to also appear in that window. So it's kind of observed minus expected. OK, so that was, in all its gory details and all the way down to derivatives of an inner product, how we would take the derivatives of this entire system. But of course, that was just one example for one center word with one of its context words. Now, for the full sum, we have here, of course, a sum over all the context words, as well as a sum over all the windows and all the context words. But hopefully, that was kind of intuitive in terms of how you actually maximize the overall likelihood and hence minimize the negative log likelihood of this. Any questions? So we've done it together, and some subset of people raised their hand and knew what each next step was, but I'm sure the people who didn't have some questions. Yeah?
Could you re-explain the intuition behind the expected? You said it was like observed minus expected. Could you go for the expected part again?
So you can think of this as like an expected value where you multiply probability with the values that you have here. So each of this ux is a vector, right? And this, it's weighted by the probability that you would actually observe this word's vector in around this center word. So that way, in each update step, one basically will become more and more similar. And once you intuitively have the perfect probability for that word is actually perfectly correctly in that right place, then that word would also have probability of 1, and you don't need to update that word. So in that point, you're done. You put perfect 1 probability onto, intuitively, the right exact word that happened to be in that context. Yeah?
This might be a hard question to answer in class, but are there any issues with the softmax function in the sense that if you were to minimize it, there's actually multiple minimums because one of the vectors is sort of redundant?
Great question. So in almost all these cases, we actually don't have convex functions. So this is also not a convex function, and we basically will always just in pretty much every neural network that we look at will be stuck in local optima, and we're usually okay with that. And we'll talk about that a little bit more. Okay, so if some of this did go too fast, now is the best time and only time to really keep on top of everything. And so I encourage you to derive the gradients for the outside vectors u. And you'll go through very similar steps, but you sort of start gaining familiarity with it. Because by the midterm, you want to be able to do these kinds of things really, really quickly for much more complex functions. And we'll get to those complex functions. We'll help you with them. OK, so now, so far, I've told you this whole thing that we have these 2 vectors. It turns out that's just an easier optimization problem. If you have in the exponent a quadratic function, you can kind of think of that as being much, versus like a bilinear type function, much sharper valleys. So intuitively, when you have a lot of quadratic things, you might look more like this. And that's just intuitively a little harder to optimize as you have very non-convex kinds of functions. But in the end, we'll actually, once you want to just have a downstream like machine translation system, you want to give me a vector for a single word, turns out we're just going to average the 2 vectors. Some people also concatenate them, so you have a 2D vector. There are lots of different things you can do, and in most cases, they won't have like, this is the obvious theoretically right answer. You just try them, and you see which one works better. Now, I also described to you the skipgram variant of word2vec. There are actually other variants where you basically, instead of taking the center word and trying to predict the outside words, you take the average of the outside words and you try to predict their center word. Very similar idea. They actually turn out to work very similarly. In some metrics, one works slightly better than the other. But you can actually, and you will, derive the continuous bag of words, the second variant where you predict the center word. You'll derive that in the homework. Yeah.
Since you average them in the end, like the 2 copies of each vector, do you initialize them as like the same value to begin with, so they kind of get stuck in similar local optima?
That's a good question. How do we initialize all these word vectors? And in most cases, you actually want to initialize them very randomly. And we'll go into a lot of details because initialization of a lot of non-convex optimization problems becomes an issue. But in most cases, you have something like this where you just initialize them all as uniform random numbers between 2 small values. So you don't want any kind of symmetry by keeping things the same or all the values the same. It's just a bunch of very small random numbers, and then you go from there.
For both copies of the vector?
For both, yeah. Both will just be random. OK. The other one, and hopefully we'll get to that in the next 12 minutes, is that we'll actually also look at negative sampling. So you might think every time you want to update one vector here in this equation, you have to compute this entire sum. But this vocabulary could be 100 or 500,000. Each of these vectors is maybe 100-dimensional. So you have 100-dimensional vectors in their inner product times 500,000. Every time you look at one pair of words, that's a lot of computational cost. And ideally, you want to avoid that. And the only way you could implement this and train it in a reasonable amount of time is by actually avoiding it. And that will be part of the problem set. And I'll go a little bit over that after just kind of wrapping this one up by talking a little bit about gradient descent and how we're going to optimize this. So again, what is this training procedure overall? We basically look at each window, and now we've collected all the gradients for all the center words and their respective context words. And so we have this overall cost function that we want to minimize. And we'll just use gradient descent for this. And again, we have some just quick refresher of gradient descent. We have a current value theta for all our parameters, calculate the gradient, and take a small step in the right direction. And we'll just keep repeating that. So if we were to have a simple convex function, it will look like this. And we could always guarantee that we'll be in the global local minimum, the global minimum of this function. But in all our cases, you can intuitively think of these functions not like this, but more like this. They're crazy. They're all over the place. And the deeper the networks will be, the weirder they will look. And there's a lot of complexity around this optimization, and we'll go into some of that, but we won't go, it's not an optimization class. But we'll think a little bit about this. So if you had 2 dimensions, you'll see this. And what we'll actually sometimes observe is that locally, they can also look like this, but then just the overall global shape of the function is not as nice and convex as this. So in almost all cases, we can guarantee that we'll derive, once we're in the vicinity of such a local optimum, we'll arrive at the bottom of that local optimum. All right, so now in gradient descent, we'll have to think a little bit about this computationally as well as mathematically. The update equations in general for overall gradient descent is we want to compute our new set of parameters, take the old ones, minus our step size times that gradient. And we take all these little steps one at a time. And so our overall update equation for a single element of that vector is just basically this. And if we were to write this in very simple Python code, this is literally 2 lines of that code. We evaluate your gradients for a certain corpus with all our parameters and our objective function. And then once we have that gradient, we'll just do theta equals theta minus alpha our step size times that gradient. So this is just a large vector operation. Now, what could be the problem with this for, say, a large corpus like Wikipedia, when we actually want to train all these parameters? Yeah?
How of a large corpus that is large?
That's right. Problem of a large corpus is it's large, and you will encounter large corpora. And then why is that a problem for optimizing it?
We're going over everything.
That's right. So you have to, in order to compute the full J here, which again was that sum over all the context windows and each context windows, inside words, that will take you essentially a couple of potentially days, especially if you don't have the optimization yet. And so only after many, many computations will you take any kind of update step. And it's probably a good update step, but you can only take so few. And so instead of doing full gradient descent, we will, in pretty much all cases in this entire class, always do stochastic gradient descent, where instead of going through all the examples of our corpus, which in theory is the objective function we always want to minimize, we'll actually just update our parameters after every single data point that we see, or in some cases, we'll so-called batch them. We take 10 examples, 10 windows, we put all their gradients together, and then we make a quick update step. It turns out that that works better in every case for this class. So in our case, where does the stochasticity come in? We'll essentially sample all these windows from the corpus, and we'll make an update right away. And in each window, we'll only have certain sets of word vectors, right? But in a very abstract case, we'll take a window, we sample it from the corpus, then we'll evaluate the gradient only on that window instead of over all windows, and then we immediately make an update step. Now, intuitively, this theta has all the vectors in it from all the words, right? V for aardvark all the way to V for zebra, and then U for aardvark all the way to U for zebra. But of course, this will be very, very sparse, right? The gradients are 0 for all the words that don't happen to be in that one window. And you can actually be smarter about it. Instead of summing up a bunch of zeros, eventually you can have a nice hash map and just like find that particular word vector and then update it. Lots of clever things you can do computationally, but that is the main idea for stochastic gradient descent. Now in the last 5 minutes, I want to give you a little bit of a heads up and walk you through the first problem set and the equations in that one. Now, instead of having this complex softmax, which has to sum over all possible word vectors in the entire vocabulary, so every time you wanted to get the derivatives for one window, you'd have to, at least for a small window, like with 2 words on each side, you have 4 of these. 4 times you'd have to sum and run an exponent over all, and then this large inner product over all possible vectors in the vocabulary. That is very, very slow. And it turns out what intuitively you're telling your model there is that when you say like the zebra is running around, that zebra is like not next to aardvark, and it's not next to computer, and it's not next to all these other words, and it's kind of redundant. You don't learn that much by telling that the context words at this context window are not these other 500,000 words. So intuitively, what the original paper from Tomasz Mikolov here did in 2013 was to actually just subsample a couple of words and then reduce their probabilities. And so instead of having a softmax over the entire vocabulary, we'll just have a very simple sigmoid function, which will also become our friend. We'll use sigmoid functions in a lot of places. And the sigmoid function is a very simple function that maps any real number to be between 0 and 1. And again, that's good enough for us to be able to call it probability. And what this is intuitively doing here is to essentially, and this is the type of equation that you'll actually see in this original paper, but to make it a little easier for us, we'll sort of map it to the notation that we just used that is easier to understand. What you'll intuitively do here is you have this probability now for the center word and its context word, and you want to maximize that probability and hence minimize the negative log of that probability. And then instead of summing over the entire vocabulary, you're just going to take k examples, like 5 or 10 random words, and you just say, I want to minimize the probability that these 2 words co-occur together. And it turns out that way you can make even more update steps. Each update step is probably not quite as accurate, but you can make a lot more of them, and on that trade-off, this works out to be much, much more accurate. So you just basically, instead of saying, I want to minimize all the probabilities for an entire vocabulary, you just take 5 or 10 examples, and then you basically make sure that this really still works. So this word really appears in that context, and these 5 or 10 others don't. That's intuitively what the final thing is capturing. Any questions about this? Yeah?
Sample 5 or 10 other words essentially at random from the source?
So that's a good question. How do we sample these 5 or 10 other words? We'll actually look at the unigram distribution. So more frequent words might be sampled more often. And then and this is kind of hacky, and just kind of by trial and error, I raise it to this power of 3/4, which essentially pushes the less frequent words to be sampled a little bit more often. So the more often words appear, the more likely they're also going to be pushed down as unlikely words in that context if they indeed do not appear in that context. So in problem set 1, you'll implement this. You'll also, as some bonus points, I think, implement the continuous bag of words where you predict the center word given its surrounding words. And hopefully, once you've done that problem set, all of this will be very clear. And again, it's a super important first step, both in terms of the math and getting up to speed, and implementing gradient descent for the first time, having your objective function, and all of that. So there's a lot of content in this lecture, and hopefully you'll be all excited to see more in the future.